Thank you for the very kind introduction. It's a pleasure to be here. So the outline of this talk is the following. So first, I'll review how we think about black holes as quantum systems, or what this hypothesis is. Then we'll talk about the Schwarschild wormhole. It's a very concrete wormhole, and the relationship to entangled states. Then we'll talk about traversable wormholes. And then I'll discuss some aspects of spacetimes that have an ADS2 geometry and some relationship to some simple condensed matter-like systems like the SYK model. And then I will discuss a traversable wormhole solution in 4 dimensions. So the idea of black holes as quantum systems is the following. So the idea is that if you look at the black hole from the outside, it can be described as a quantum system with a finite number of degrees of freedom. So a finite number of qubits. You can view this as a hypothesis, or you can view it as an assumption. Let's say for the parts of the talk, this will be an assumption. And we have various reasons for thinking that this assumption is correct for black holes in nature, for black holes in any theory of quantum gravity, that this should be the case. So one reason for this is the ADS CFT correspondence. So the idea is that if you have an ADS spacetime, which is a spacetime with constant negative curvature, I will not explain all the details of this because we will not need it. The idea is that those spacetimes can be described in terms of a field theory of a ordinary quantum system that lives on the boundary very far away. And if you have a black hole in that spacetime, then that black hole is described in terms of a fluid of very strongly interacting particles, and the entropy of the black hole is the entropy of the fluid. And the quantum mechanics of the fluid is ordinary quantum mechanics, and that's supposed to be describing this, not only the black hole, but the black hole and the whole spacetime from the outside. And there are more recent toy models, which I will discuss a little later, just to understand this phenomenon in its, at least some aspects of this phenomenon in a nice, simple way. This is some model of N interacting Majorana fermions. As I said, I'll discuss it later. And they have many properties in common with near extremal charged black holes. I, again, will discuss what they are later. Now,
a lot of us, when we were young, were taught that black holes didn't have any hair. And you give us a picture of a black hole with a lot of hair. So how do we reconcile what we were taught as children?
Yeah, so these no-hair theorems are for classical physics and are for somewhat restricted classical physics. In fact, people have discovered that when you think about more general theories, you can have even classical hair. But the simplest form of, if you wish, of some indication that the black hole is not as simple is the phenomenon of Hawking radiation. And so when you have Hawking radiations, the black hole is not just, doesn't look like a simple solution, but it looks like a gravitational solution with some temperature and some thermal state around it. And so once you include these quantum effects, you see that you have to describe the black hole, if you remain outside, as a thermal system, and there will be a density matrix that describes it. And the statement about the hypothesis I just made is that there is some quantum system that where the black hole has some finite entropy. In the approximation, in the semi-classical approximation, so the approximation that Hawking worked with, so where you have space-time plus quantum field theory, then the naive entropy is ultraviolet divergent. So it cannot be computed in ordinary quantum field theory. And this divergence arises because the state of the quantum field is entangled between the outside and the inside of the black hole. And when you say you remain outside, you only observe the outside. And the total entropy of that outside is infinite. That infinity arises whenever you have quantum field theory and you divide the spatial system into 2 parts. There is an ultraviolet divergence. But then at the same time, we have the black hole entropy formulas, which say that the entropy of the black hole is the area of the horizon in Planck units. So the basic idea is that this divergence may be somehow, in a way we don't completely understand. It's regularized by the Planck scale, and we have a finite entropy, which is given by just gravity already knows about that and gives us that finite entropy. And through some formulas in string theory and in simple models with some supersymmetry and so on, you can count some of these quantum states and get an entropy which agrees with the Hawking formula. But it's somewhat indirect, so the connection between the space-time bulk picture and the entropy is not direct. So there's a lot of evidence that this idea, the first idea and this idea we mentioned here is correct, and I'm not telling you. So the evidence through theoretical models and toy models with a lot of symmetries that we can solve, and so we'll make this assumption. And so this is an assumption about quantum gravity. So that in quantum gravity, a black hole can be described from the outside as a system with a finite number of qubits, and which undergo a unitary dynamics. So the fact that the black hole has no hair, you could say that is equivalent to saying that a black hole is a thermal state with very few conserved quantities or no conserved quantities other than the total energy, and that any small perturbation quickly settles down into a thermal featureless state. It's featureless because you're not keeping track of all the macroscopic dynamics. Okay, so this is transparency, sort of reminding you of what the geometry of a black hole that is made from collapse looks like. So we represent the geometry in terms of these diagrams, which are called Penrose diagrams. And these are diagrams where where light rays move at 45 degrees. The vertical direction is roughly time, and the horizontal direction here is roughly the radial distance from the black hole. Here we're imagining a situation that is spherically symmetric. We're imagining a star that collapses into a black hole. And when that happens, if you are at the surface of the star, you don't feel anything special and until you get to a singularity, a region of infinite space-time curvature. So a black hole has a region outside that is given by the so-called Schwarschild metric, and a region inside which looks like a collapsing universe. It looks like a big crunch, essentially, where the two-sphere, the size of the... So there is, at each point in this diagram, there is a two-dimensional sphere, so this is the sphere you have in flat space at the fixed radial position. You have a two-sphere, and that two-sphere has finite size here at the horizon, but has zero size at the singularity. Okay, so that's this is a solution, and this solution shows that someone who's sitting at the star doesn't feel anything special when he crosses this particular surface. So this surface is an imaginary surface, imaginary in the sense that someone who crosses it doesn't feel anything special, but it's a surface that divides the points that can send the signal to the outside from the points that cannot send the signal to the outside. Okay? So the best you can do is send the light ray at 45 degrees, and here the light ray, if you start from the interior, ends at the singularity, and if you start from the exterior, you can really reach infinity. Okay. So that's the solution. So this is a solution when you have matter. So the solution outside is the Schwarzschild solution when you have the vacuum, and the solution inside is different because you have matter. But there is the full Schwarzschild solution, which is to take the solution that Schwarzschild originally found and extend it analytically as much as you can. Okay? And it took many years to really understand what the full geometry is. You can say it's surprising how much time it took. One of the first papers to realize that, well, okay, so the geometry is the following. So you have some region that looks like the exterior of a black hole. This is the region that was originally covered by the solution, by the coordinates that Schwarzschild chose to write his solution. And then people then realized that it was connected to the interior. Those were these first papers. Then Einstein and Rosen realized that if you take a spatial section, that spatial section actually is connecting one exterior to a second exterior. So actually the solution contains somehow two black holes in two separate universes that they are connected through the interior. Einstein and Rosen thought that the horizon was singular, and they made some apologies for considering a singular solution. So they didn't read these previous papers where they had found coordinates where it wasn't singular. And then eventually people understood, and the one who really understood this diagram was Schwarzschild. And that's the full classical solution in its complete form. So we have two black hole exteriors that share a single interior. So they live in two separate universes. They are connected, and they share a single interior. It's a vacuum solution, so it has no matter anywhere. So it's a solution of just the equations of general relativity. And in some ways, it's the simplest solution. It's the simplest because it was the first that was found. And it has no matter, and it has spherical symmetry. So one of the simplest and most symmetric solutions of general relativity. And part of the question we are going to try to understand now is what its interpretation is. Now, this type of structure is very generic. Whenever you have a black hole, simple black hole solutions, you typically get actually two black hole solutions.
Yeah. What solution here should I think of that as an exact solution to some partial difference equation?
Yes, yes,
or
yes.
What solution needed? That's
Yeah,
exactly
yeah. So we have the Einstein action, which is well, it's the standard Einstein action. The standard Yeah, so we have the standard vacuum Einstein equations, which are the Ricci tensor equal to 0. And you solve these equations. That's what Schwarschild did. Purely mathematical statement. You just take a situation with spherical symmetry. You plug in that metric here, and you find the solution. So it's something, yeah, the first thing you would try, and, well, that at least Schwarschild could try. And he tried it and found the solution. He even found the solution in his spare time while fighting the First World War. So, and, yeah. No, yeah, that's the beautiful thing of general relativity. So there is no mass anywhere. There is no energy density anywhere. Far away, there is a notion of mass that you can calculate by using Kepler's third law, right? So there is some object in the center which attracts stuff that's going around, but the solution contains no mass, no ordinary mass or ordinary matter. It's always locally equal to the vacuum. So somehow this mass is purely due to the curvature of space-time due to connecting to this other universe. So it's a pure black hole. No, it's a very simple object. It's like a Platonic solid, right? Very symmetric, simple geometry, basic geometry, the solution of simple equations. So it's a basic Lorentzian geometry, if you wish. Okay, yeah, maybe I'll emphasize this. Normally, people think of a black hole as, well, some funny thing, and there is something in the middle. That's where the original stuff that made the black hole is. But the original stuff that made the black hole is not somehow inside, or the singularity with infinite curvature is not somehow inside, but it's in the future. So even in this previous story, it's here in the future. The interior looks like a cosmology, and the singularity is in the future. And you can't escape it because you cannot travel to the past. So for some reason, you cannot travel to the past. You can't escape falling into a singularity once you are in this region. Okay, and this type of structure is similar for all black holes, where there are black holes in flat space, black holes in anti-de Sitter spacetime. They have, in anti-de Sitter spacetime, you have very similar diagram. The only difference is the asymptotics of the geometry is slightly different. So, now, then there is a closely related solution. It's not exactly the one that Schwarschild found, but it's a solution that is very similar. So the one that Schwarschild found had the two black holes in two different universes. But you can take a solution which is rather similar, where the two black holes are in the same universe. So that solution is not exactly spherically symmetric because you have to choose the direction in which to put them. But near each black hole is close to a spherically symmetric. And near the two black holes, the solution is very similar to the solution that Schwarschild found. So this diagram now does not describe the full solution, but the solution that includes the space-time region near one and the space-time region near the other. So if you consider only that space-time region, and you ignore the full space-time that connects them, you find the geometry similar to the one that Schwarschild found. So this has the geometry of a wormhole. So this, again, you have this Einstein-Rosen bridge where the geometry looks like the geometry of flat space, and then it contracts, right? The sphere reaches a minimum size and then connects again to the other region. So, I mean, these two black holes could be very far away. Let's say one is here in the Milky Way galaxy. The other one could be in the Andromeda galaxy. And yeah, if you are 1 meter outside this black hole, you are separated by a few million light years from a person who's 1 meter outside the other black hole. But you are separated just simply by 2 meters through the wormhole, okay, in this particular geometry. So this would be a person here and a person here separated by 2 meters in the wormhole. So they're very close to each other there. But nevertheless, you cannot send signals through this wormhole. So if you try to send a signal, the wormhole sort of starts expanding, the two horizons start separating, and the signal goes in and ends up on the singularity, and doesn't manage to go to the other side. Yes? Is it? Yeah, say the question. Yes. It's, well, the way I described it as an approximate solution. And there isn't an exact solution that I know that has this form, but you can set up the initial conditions that will lead to a solution of this form. So, yeah.
I'm wondering if this solution without matter is what your theory on top of it will get Hawking or something like that?
Yes. So when we have this solution, for example, we can put a quantum field on this solution, and we can put a quantum field, and you have to choose the state of the quantum field. And so,
where does the energy come from? Is there no matter at all?
well, there is a quantum field, right? And the reason you have Hawking radiation is because you are dividing the state of the quantum field into 2 parts, right? And there is one special state that people sometimes consider in this situation, which is the so-called Hartle-Hawking state. And there, the quantum field is in thermal equilibrium, and the black hole is in thermal equilibrium with the outside. So it's a special situation where the symmetries of the quantum field also reflect the symmetries of this situation. And so this setup has a boost symmetry around the origin. And yeah, so that's a special state you can choose. But you don't have to choose that state. Yeah.
Could you explain what you mean when you say 2 universes?
Yeah, so this solution contains 2 asymptotic regions that are asymptotically flat space. Imagine 2 4-dimensional flat space regions. So first consider 2 universes, right? So we have a 4-dimensional flat space universe and a second one, completely disconnected from each other. So if you start in one, you'll always remain in one. If you start with the other, you always remain in the other one, right? But now you can connect them by choosing a geometry that connects the 2 universes. And one interesting point that I'm making is that there is a solution of Einstein's equations that has this geometry that connects 2 separate universes. Right? Now you might say, well, I need to have started with 2 separate universes, so maybe I don't want to consider the solution. So just to make it a little more similar to things we know, I'm just discussing now the case where the 2 black holes are in the same universe. So I discussed the one with 2 universes because that was a solution that Schwarschild found. So, and then now I'm trying to discuss related ones that are just in one universe. And you might be worried about these solutions because you are creating a short geometric connection between 2 points, 2 faraway points, and you might think that you could get causality violation, right? And one of the cornerstones of special relativity and general relativity is that you cannot send signals faster than light. And it would be funny if the theory that itself then predicted that you could send signals faster than light. And it turns out that you cannot. So you cannot use these kinds of solutions to send signals faster than light, and that even if you put matter that obeys, that is consistent with reasonable principles, you can also not do that. So more technically, it's called if it obeys the average null energy condition. So standard matter does not allow you to violate this. By standard, I mean standard quantum field theory. Yes.
So these solutions, when you have these wormholes, is there a simple way to understand how they could be created?
That's a very good question. Yes, for now I'm saying suppose they are there. And yes, we'll discuss that if it's not clear by the end of the talk. We'll discuss how difficult they are to make. Okay, so the idea is that this type of solutions should be viewed as 2 black holes whose quantum states are entangled with each other. Okay? Okay, so we said before that let's accept the hypothesis that the black hole can be replaced, as viewed from the outside, can be replaced by a quantum system. Right? So
you're making a jump now because
I'm making.
you talked about general
Yes.
relativity. Now
Yes.
you want to impose this cubic picture.
Yeah, we're imposing that. So that cubic picture with the black holes, with the qubits, we don't know how that is consistent with general relativity. So that seems to go.
That will accept. So now
Yes,
you're
yes.
introducing quantum mechanics
Yes.
to that hypothesis.
Yes, that seems to go beyond general relativity, and maybe it is in some way consistent, but we don't know yet how it is consistent.
But I just want to make sure I
Yes.
understood. But given
Yes.
the hypothesis, now
Yes,
you're
yes.
quantum mechanics.
Yes, yes, yes. Yeah, so if you accept that hypothesis, then there is a picture for what the quantum states are for these geometries. So the idea is that these geometries would arise when you have two perfectly entangled states, black holes, that are entangled in a very special state. It's a state that is called the thermophile double state. So thermophile double state is a state you can make when you have two identical quantum systems, and you take all the energy levels of one quantum system, and you entangle them with the energy levels of the second quantum systems with weights which are similar to the thermal weights. They differ just by this factor of 2 from thermal weights. And it's called thermophile double because if you trace out one of the systems, then you get a thermal density matrix for the other system. And it's a state that had been considered before when people describe or consider thermal field theories. So it was a state that was considered for mathematical reasons previously. And so this is an example. Okay, so this is something that arises when you have this particular entangled state, but we think that if you start making changes to this entangled state, then you will make changes to the wormhole that connects the two.
So what is entangled? What I'm worried about is these two live in the same universe. So
Yes, yes.
Just draw planes to them, and they're
Yes.
entangled.
Yes, yes, yes. So if you were to divide space-time here in the middle, there would be high entanglement due to the quantum fields, but that entanglement is mostly short-range entanglement, right? So the idea is that you have here lots of qubits, and there is a long-range entanglement between these two qubits, the sets of qubits that make the black hole. As I was asked before, how you make them, I'm not discussing. So this shows that, at least this picture shows you that it will be pretty difficult to make it because you would need to entangle the systems very highly. Yeah.
From optics background, so can you just define more why the finite dimensional system instead of unidimensional
Yes,
system
yes.
with finite entropy and entropy?
Good, yeah. So here, the assumption is that the relevant number of degrees of freedom is finite dimensional. So that the only content of what I'm saying is that it's the entropy is finite, right? So the full system of the black hole and the space-time around it and so on is likely to be infinite dimensional because the space-time is infinite. But the idea is that you can effectively separate the finite number of the degrees of freedom for the black hole. Does that answer your question?
So then, what about the Hawking radiations? Like they use like some
Yes, yes. So yeah, Hawking radiation and the degrees of freedom associated to it have to do with quantum fields in the space-time, and I believe you think of that as being infinite dimensional. But the idea is that quantum fields in a space-time is a good approximation as long as the fluctuations and let's say the mode numbers of the fields or the frequencies of the photons are smaller than the Planck scale. Okay? And so the idea is that effectively the theory has some kind of cutoff, which is of the order of the Planck scale, and that puts a constraint on how big the Hilbert space is. Similarly, each mode, like in optics, is a harmonic oscillator. In a harmonic oscillator, you can excite it infinitely. But the idea is that if you excite the harmonic oscillator too much, at some point you'll make a black hole, and that description will not be valid anymore. So here, the idea is that gravity puts a limit on the entropy that you can store in the system.
Is it a hard cutoff?
Well, it's a cutoff whose precise nature we don't understand. I mean, so that's why I phrase it as a hypothesis. That when you have a black hole of a given area, given size, the total number of degrees of freedom that you need is proportional to its entropy. I should probably emphasize that this entropy is very big. So the entropy is equal to the area divided by L Planck squared. And L Planck is a very small quantity of 10 to the minus 33 centimeters. Okay? So it's a very big entropy compared to the entropies of ordinary macroscopic objects.
And so the number of the equivalent number of qubits is also very large.
Yes, yes, yes. This is the number of qubits. This is roughly the number of qubits.
So roughly a gazillion.
Yes, gazillion, yeah. Yeah. So we are talking about very big numbers, at least so far. When we are talking about ordinary four-dimensional gravity, we are talking about very big numbers. But one can consider alternative theories of gravities. And this ADSE, maybe we'll discuss another specific model later. But maybe just one of the ideas is that some more ordinary-looking systems might have a gravity description through some weird theories of gravity. Okay, and so that ordinary systems and gravity theories are closely connected. So ordinary theories are weird gravity theories, and ordinary gravity would be a weird, again, quantum system, or at least some. Okay, so the idea of ER equal to EPR is that this entanglement and geometry might be connected more generally. So even for ordinary systems, there might be a weird theory of gravity where this happens. So this is not a concrete mathematical relationship. This is a sort of a vague idea like that might be true. The idea is that this could be true once we have a full quantum theory of gravity that describes any system. Now, I like to usually tell this story. I'm sorry if I told this story already when I was here last time, but I'll tell it again. Just trying to explain what it means for this geometry to share an interior. So usually wormholes are discussed in the context of science fiction. So the ordinary science fiction story does not work for these wormholes because they are not traversable. But we can have an alternative science fiction story where we have two people, let's call them Romeo and Juliet, and they like each other, but their families don't like each other, and so they take Romeo and they leave him here in the Milky Way galaxy, and they take Juliet to the Andromeda galaxy. But they are very smart and resourceful, and they live far in the future with very large technological possibilities, with very strong quantum computers that you guys will help build. What they do is they exchange messages, and the messages consist of qubits that are entangled. So they create a bunch of entangled qubits, they share them, and they collapse them into black holes, and they manage to manipulate these black holes with these wonderful quantum computers that you will build, and they create the black holes in this perfectly entangled state, the thermofield double. So, and after they are done, they each have their own black hole, but the geometry of the black hole has this space-time geometry. So then at the prescribed time, they decide to jump in, and let's look at the bottom picture here. So they jump in, and they each fall into the black holes, so their families feel that they have committed suicide by falling into a black hole, and the narrator of the story also felt the same way. But that's not what happened to them, so they just jump into the black hole, and they meet inside the black hole, and they live for a while inside the black hole. Unfortunately, they die. So
just
this,
because of the tidal forces, or what?
yeah. So, well, so they die when they get here to the singularity. Now, this is really, in order for you to survive falling into one of these black holes, it needs to be a very big black hole, like a supermassive black hole. Even a black hole of a stellar mass, you wouldn't survive the tidal forces of going through the horizon. No, your information could survive. So yeah, your information could survive, but they were not interested in only that. So yeah. So I guess you're asking. So the question is whether there is a better way, okay? And there is a way in which you can create a better story. So I'm now trying to improve. We'll try to improve the story, and this is based on some very nice work by Bagao, Jeffries, and Waals, who found a way to improve this story. So before I tell you about that, I'll have to, probably I don't need to remind you what is quantum teleportation. Who needs a reminder of quantum teleportation? No one here. Okay, so you know quantum teleportation. So the idea is that, well, let me say a few things. So I need to say, I need to just to establish the language, perhaps. So we have an entangled state. We have a qubit we want to send. You measure the qubit you want to send with the entangled state. You do a measurement. You send classical information. And you do some operation, and then out comes the message. Okay, so that's standard quantum teleportation. Now the question here is whether you would like to be teleported. Okay. Now, so this is, we replace the message by you, and then there are a bunch of entangled qubits, and then there is this measurement that's supposed to be done, and that sounds a little unpleasant, because here there is some unitary that's supposed to mix you with the entangled qubits, and this doesn't look like a very good experience. Now, you are guaranteed that you will be reconstructed on the other side. Right? This is a bit like when surgeons were experimented with anesthesia, they found that maybe there were some kinds of anesthesia that make you forget the pain you suffered during the operation. So the question is whether you would sort of like to undergo anesthesia under this kind of circumstances. So the question is where you can, now, what Gao, Jeffreys, and Waals realize is the following. So you can imagine a situation where you have two systems that are some quantum systems that are entangled, that have a gravity description, and we have a geometry with the shape we discussed, the wormhole geometry. And in a situation like this, if you drop a message, so here we are dropping a message on one of the black holes, and then we do a measurement here on the left system. We do some measurement here. And this measurement is, we are just really measuring the Hawking radiation that comes out of this black hole. So we drop something into the black hole. The black hole, sort of, this object becomes in thermal equilibrium with the radiation. You do some measurement here. And then you send a classical message to the other side. And the other side sends a signal into the black hole that, because it's correlated with this one, it manages to extract some energy from the black hole and send a negative energy pulse to the black hole. And what that does is it manages to extract the message out. And this happens because if you have, in general relativity, if you send an ordinary positive energy pulse and another pulse crosses it, you always suffer some time delay. This is a famous general relativity effect. It's kind of related to bending of the light by the sun in this case. So that's one effect, but the second effect is that light also gets a little later, some small time delay when it passes a massive object or some energetic pulse. But if that pulse had a negative energy, then instead of a time delay, you have a time advance, and you can exit this black hole, and the message can come out. And so they show that the standard teleportation protocol would would have this space-time description once you view it through this wormhole. So it has a representation as information transferred through the wormhole. So the interesting aspect is not that information can be sent, because we are already sending some classical information. The interesting thing is what this message feels as it undergoes this process. So it's really all about feelings. Okay. What does the message feel when it crosses, when it undergoes this? Well, it feels at least some kind of shock wave when this pulse crosses here. But you can arrange this so that it is relatively painless. And this can be arranged if you arrange the measurement to be spherically symmetric. So in this situation, you can Romeo and Juliet can come up with a different protocol for meeting each other, which is a little more, has a happier ending, where Romeo jumps in the black hole. So they make the black hole the same way they made them before. Romeo jumps in and arranges for the computer to measure the Hawking radiation and send the signal, the classical signal, to the other side. And here, Alice manipulates her black hole so as to extract Romeo out of the black hole. Okay. And Romeo can report that he saw a smooth interior. didn't feel anything bad. Yes.
I guess when you use teleportation, right, the number of sort of classical systems
Yes.
sort of how, well, I guess the number of
Yes, yes,
so
yes,
then
yes.
I guess Romeo likes to consider itself as classical, then doesn't classical.
Yes, yes. So the number of qubits you need to send the Romeo is astronomical. It's super high. So this is all theoretical. Okay, it's just to make a nice story, because in fact, so the number of qubits is related to Romeo's rest mass in the background of the black hole. More precisely,
This cannot be done with Alexis 52 qubits.
no, no, no.
Or even if he makes it 53.
Yes, yes, yes. So it's basically you have to take Romeo's mass, rest mass, right, and then multiply to the basically the size of the black hole that we are talking about. And so this is a very big number. I didn't put factors of the speed of light and so on, and h bar that make this very big. Okay. But maybe we cannot do it with Romeo, but perhaps we can arrange for a lab system which realizes some systems, and instead of sending Romeo, we can maybe send a couple of qubits or things like this, and ask some questions, asking these qubits what they felt when they went through. So we'll have to translate this into some appropriate mathematics of what it means to ask them what they felt. So the interesting point about all of this is that Romeo can report and really felt that he went through a smooth interior, while the quantum description from the outside might make you think that Romeo suffered something terrible because he was mixed with a bunch of other qubits and underwent a measurement. Yeah. Yes. Yes. Yes, 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 yes. No, that's a very good question. And so the idea here is the following. Imagine that these two are some laboratory systems, some very sophisticated quantum computer that realizes this gravity theory in the interior. So gravity theory in the interior is not the gravity theory in our own real world, but it's some, let's say, other gravity theory. And then in the lab, you can send signals very fast. So the speed of light here is faster than somehow the time it takes to go through the interior. And so that is what allows you to send this signal. So this causal diagram that is here is only a portion of the total causal diagram of the space-time. In here, this space-time is patched onto the rest of the space-time through some shorter connections outside. Okay, there is no violation of causality here. The only special feature is what Romeo feels. So it's about his feelings again. And we'll later, I guess I'm running slow, but I later will show you some solution in 4 dimensions in our own space-time that has similar features. Yeah. Yes. Well, so what you can have is the following, and I'll discuss maybe this a little more later. So you can have a situation where you have 2 black holes, right? And then you have some wormhole. And what is necessary is that the distance through the wormhole is longer than the distance through the ambient space. And you can have solutions that do this. Okay? And that's roughly what we have in these situations. So we can send the signal faster through the outside and through the interior.
Okay, there will be no more questions for the next half an hour because I want to get to the end. And then we have questions.
No. I think it's good to have the questions. So yeah, I don't mind the questions.
So no questions I didn't.
Yeah. Okay, so the conclusions I skip. Now I'll discuss a little bit some cases of near extremal black holes. So near extremal.
One question you made.
Yeah.
As usual, and I still can't get over it that in principle one can think about sending 1 or 2 qubits. Can you elaborate on that? You still need a wormhole somehow, right?
Yes.
We need to create those somehow. We need to have an experimental analogy for those objects.
Yes. So let me try to give you an experimental analogy. So one of the simplest that has been proposed. Okay. So, but before I tell you about the experimental analogy, let me tell you about some kind of black holes, a special kind of black holes. And these are the so-called near extremal black holes. So these are black holes which have some charge, and then the mass has to be bigger than the charge, and when the mass approaches the charge, they develop a kind of scaling symmetry. They're sort of like quantum critical systems that develop a scaling symmetry. And they develop a region in their geometry which has the geometry of so-called nearly ADS2 spacetime and a two-sphere. And what will be important for us is the scaling symmetry will be related to the symmetries of this spacetime. This spacetime is a spacetime with negative curvature, so it's somehow the analog of hyperbolic space, but for Lorentzian signature, so with one time direction. So it's a very simple spacetime. So the spacetime, I'm going to ignore the sphere for what I'm going to say now, and we can focus on the properties of ADS2, which is most the thing that was unhoods. The relevant thing for us now. And so the Penrose diagram of ADS2 is an infinite strip. So there are two, so the time direction goes vertical, and then there is a space direction. And that's an exact ADS2 space. But when you have a near extremal black hole, you only get a portion of this space. And so it looks like ADS2 for a region, and then there is a red line which marks the transition between this ADS2 space and the full four-dimensional flat space. Okay, that's the transition region between the two. And all of the gravitational dynamics of ADS2 has to do with the location of this demarcation line. So where you go from the near, let's say, horizon region of this ADS2 region and the rest of the space-time. Okay? So that's, and so the point of this slide is to say that gravity in 2 dimensions in this particular context, well, gravity in 2 dimensions is always very simple, and in many cases solvable, and in this case also solvable, and it reduces simply to the location of where these boundaries are. That's all of the content of quantum gravity in 2 dimensions. That's related to the fact that we don't have gravitational waves in 2 dimensions with spherical symmetry. Okay, so that's one system, and then we have another system, so a simple toy model, which is the SYK model. And this model is a model of n Majorana fermions with random all-to-all interactions. And you have a number of fermions which is large, and the n, which is the number of fermions, plays the role of 1 over g Newton. So the larger n is, the more classical somehow the description will be. And we can analyze this in some regime, so some regime of parameters. Don't worry too much about that. And so the model is, has a finite spectrum, and this is the energy spectrum. And we typically focus on the low energy spectrum, where we have relatively low energies, but we don't look at the lowest energy. We just look at the bunch of states at relatively low energies. And so in such a way that there is an exponentially large number of states contributing to the low energy region we are considering. And so the dynamics in that region can be summarized in terms of an effective action, where you integrate out the fermions and you replace them by some other classical variables. Don't worry about the details of what these variables are. The important point is that the parameter n, the only really important point for now is that the parameter n appears as a parameter in the action, not as the number of fields or as the number of fermions, but as an overall constant in front of the action. So it appears as 1 over h bar. So it governs the quantum corrections to this action. So in the Larsen limit, there is something that becomes classical. The thing that becomes classical are these effective variables. I was planning to give an outline of the derivation, but let me ignore that. This action has the feature that it develops a scale invariance in the infrared, and so we can have this action has a simple solution at low energies that has the form of a 2-point function of a scale invariant system. That's an approximate solution. And not only has this solution, but it has a whole family of approximate solutions where we make an arbitrary time reparametrization. And all of these have the same action. And you can view these different solutions as kind of Goldstone modes of some spontaneous symmetry breaking. And through some techniques that are familiar in condensed matter, we want to write down an action for these Goldstone bosons. think in condensed matter, you don't call them Goldstone bosons. What? What? Oh, okay. Well, anyway, so you can then write down an action for them. And the action is somehow determined by the symmetries of the system. And this is the simplest action you can write down. It's called the Schwarzian action. Was derived by Kitaev. And so n appeared as a parameter. This is an approximation of the actions that I wrote before, appropriate for the low energy limit.
So one should think of it as a large n limit of the action?
Yeah, the action already is a large n limit, and on top of the large n limit, we go to low energies.
Oh, so
Yes.
both.
Yeah, it's both large n and low energies. Yeah. And so, so then there is this analogy between this SYK model and ADS2 spacetime. So let me try to explain what the analogy is. So we have on the other hand this SYK model of Majorana fermions. We can go to low energies. And we also have this nearly ADS2 gravity and quantum fields on ADS2. So in this situation, we have quantum fields on ADS2, and all the quantum gravitational dynamics have to do with the dynamics of the boundary. And then in SYK, we have that classical effective action, and the low energy degrees of freedom divide themselves into a part that is conformal invariant, and another part governed by the Schwarzian action. And this part is exactly the same for both cases. And the other part is not obviously the same and is in general not the same. So, so the idea is that these two systems share some features in common, and they are different. They are representatives of some general, very general universality class. But in detail, some detailed things are different, but some important things and some important part is the same. And this important part determines many properties, physical properties. So the simplest one is it tells you how the low energy, the low temperature entropy behaves as a function of the temperature. It governs the gravitational back reaction. It determines the chaos exponent. It says how chaotic the system is. It's determined by, again, this action. I mean, one interesting aspect is that quantum chaos somehow in this system becomes classical. And it has to do with the classical properties of this action. And it also, this action governs how you go through this wormhole. So when you think about these experiments where you send a signal and you try to detect it to the other side, the mathematical calculation of how signals go from one side to the other are entirely determined by the scaling symmetries and the behavior of this action. So the mathematical answers are the same in SYK model and in gravity in ADS2. Yes? Yes. So on the right-hand side, it's related to the value of the Newton constant. So n is related to the value of the Newton constant.
Universal properties such as chaos, for example, are totally independent.
Yes, that's right. So they depend. So this chaos, for example, depends only on the temperature, but not on the precise value of that coefficient. Yeah. So that coefficient might be relevant for some things, like if you ask a question like this, well, how strong the effect is, or yeah. So, or yeah.
I'm not putting that question.
Yes.
Yeah.
Yeah.
So is the wormhole traversability, is this related to the Romeo story? Is that how you allow the wormhole traversability?
Yes. So this stuff here, I describe this using the ADS2 and that language. But the point I'm making here is that every word that I said there can be repeated for replacing Romeo by a Majorana fermion. Okay? So I was asked before that you could send a qubit or a fermion. We need some other fermions and so on. So we can have these other fermions of the SYK model, and then the picture would be similar. Okay? And the formulas would be the same. So you could send, instead of sending one fermion, you could say a few fermions. And then when they get to the other side, the relationship between the various fermions is somehow preserved up to some to a simple conformal transformation. So that's somehow the statement that nothing happened to Romeo. That would be a way to. Okay, so now I'm going to discuss how to make these wormholes traversable forever. And this is very simple. So all you need to do is to add a constant interaction between the two sides. Okay? And then you can have a situation where there are constant interactions between the two sides, so you can always send the signal from one side to the other. Of course, the signal has to be pretty small so that it does not create a black hole. So you always have the constraint that there should be enough information going between the information going between the two sides should be bigger than the information that goes through the wormhole, just not to violate causality. Okay, so so far we've introduced this interaction by hand, and we can understand how it arises. So one way it can arise is by having two black holes, two of these near extremal black holes that are near each other. Okay? And just let me describe it as an analogy. So we have, for example, the van der Waals interaction. You have two atoms that are near each other, and they exchange photons in the ambient space, and they lead to an effective interaction between the atomic energy levels of each of the two atoms that has the form of a dipole-dipole interaction. And so if the distance here is larger, the 1 over distance is larger than the gap between the ground states and the next states, then we will entangle all the low energy states of each atom with each other, and that will rise to a force and so on. And it allows you to do various things like walking on walls, etc. Now, this type of reasoning inspired the following solution that is a wormhole solution in 4 dimensions, now in ordinary gravity and with ordinary fields. And it's inspired, it has the shape of a drawing that Wheeler wrote of a wormhole. And the spatial geometry is that of a, the whole geometry is the traversable wormhole. So the idea is the following. One of the essential elements in this solution is the idea that you can have negative energy, negative null energy in quantum field theory. So I said before that ordinary matter does not allow traversable wormholes, and ordinary matter obeys a condition which is the positive null energy condition. It obeys that condition classically. Quantum mechanically, you can violate that condition by, I'm not explaining. Quantum mechanically, you can violate that condition if you are in a circle, for example. So if you have Casimir energy on a circle, that can be negative. And this allows you to construct geometries that classically were not possible. Some solutions of general relativity that classically were not possible. So some of the necessary elements for constructing the solution I'm going to discuss is to have something that looks a bit like a circle, to have this negative Casimir energy, and to have a large number of bulk fields to enhance the number of quantum effects. And we'll show how to assemble those steps. So those things. So we're going to discuss, before the wormhole we discussed in the beginning, the one that Schwarschild discussed, had the action purely of general relativity. So now we'll add a Maxwell field so that we have we can have extremal charged black holes, and we'll add a fermion to give rise to quantum effects. And this could be an approximation to the standard model if we are talking about very short distances, where we can approximate the fermions to be massless, and the U1 that appears here could be the U1 of hypercharge of the U1 group of the standard model. So we can have a solution which is an extremal magnetically charged black hole. So this is a magnetically black hole with magnetic charge. And then we can consider the charge fermions moving in this black hole. And so we have a magnetic field on the sphere. And when you have magnetic fields on a sphere, well, or in any kind of magnetic field, you have Landau levels. And when you have a massless fermion, you have a precisely zero energy Landau level. So what happens is that the orbital and dipole energy cancel precisely, and you have some massless fields. And so these charge fermions, they give rise to, so a single charge fermion in 4 dimensions gives rise to Q massless fermions that move along the radial and time direction. And Q is an integer, which is the magnetic charge of the black hole. So this is like a Landau level problem in condensed matter. Something similar happens in graphene if you put a magnetic field. Because it's also described by a massless fermion. Okay, so basically you have this a black hole, and then you have massless fermions that move along along each of the field lines. So each Landau level, we can think of it as localized within a flux quantum of the on the sphere, and then they move along these field lines. And so in the end, we get a picture that looks like this, where we have the magnetic field lines, and we have these massless fermions that move along the field lines. They create some negative energy that make this solution possible. And you can actually solve the Einstein's equations and show that you get a solution of this form. Okay, and the solution is controllable within some regime. And this solution should be viewed as two entangled black holes. And so from far away, they look a bit like a black hole, but when you get closer, you find that they have no horizon. So you start going into one of these two-dimensional anti-zeta regions, and they get connected to the other side, but with no horizon. So I was asked before whether it's easy to produce these entangled states. You asked me. And so one question is if you bring, so one method might be to bring two black holes, and this state that we are discussing here has less energy than two separate black holes, and so it could be that it's formed, but we don't know for sure that how fast it forms. So we don't know for sure how fast this system forms, but that would be one way to form them somewhat naturally. So you bring them close, there is some interaction between them, and the entangled state has less energy than other states, so you will fall down to the entangled state. And then you could separate them and have them separated in this entangled state. So that's might be one method to form them. Okay, and, there were some details here about the solution that I'm going to skip. Here we discussed this solution of Einstein-Maxwell theory with charged fermions, that is a traversable wormhole with no exotic matter that balances classical and quantum effects and has a non-trivial space-time topology that was forbidden in the classical theory. Yeah, I didn't explain, but even a classical wormhole like this that has a wormhole length longer than the distance between the two sides is forbidden in the classical theory, but it's allowed in the quantum theory. And it can be viewed as a pair of entangled black holes, but it has no horizon and no entropy. And there are many questions for the future, like related to the question you asked me, whether if we start with two disconnected near extremal black holes, can they get connected quickly enough or not? It would be very interesting because it's a process that involves topology change. So you have, initially the spacetime has one topology, and then in the end, it has a different topology. And it would be interesting to understand in detail how that happens. Okay, thank you.